right, awesome. Thanks, Duncan. Okay. All right. Today I'm going to be touching on some of the lab work we're doing, but one of the things that really gets me excited is when you can model something on pen and paper, simulate it, and then watch it happen on an oscilloscope. And that's really my aim, is to share that enthusiasm, and hopefully you can see it and feel that here, because we're going to be dabbling in some modeling and showing some of the underlying theory, and then see what happens when we go to the lab, and what my collaborators and students have been doing to make these things happen on hardware. Okay, let's jump into things. Let me get this to a pointer. Okay, so yeah, this is the amazing group of people that have been helping me out and really making the results happen from my students and postdocs in my group at other universities and also industry. I've been working with Enphase quite a bit lately on a recent project we have. Trying to, hold on. Oh, there we go. Okay, I also want to give credit to the Department of Energy and EERE especially for supporting me on my endeavors working on grid forming since 2015. These are the two award numbers for the projects that have been allowing me to really devote my efforts to this idea. And, just give them a lot of credit for when I first was pitching this in 2014, 2015. I think this was a kind of a wild idea to kind of rethink the whole grid, and they were willing to take that bold step and to support that. So there's a big thanks on that. And what I want to do is I feel like this audience here has gotten a lot in terms of introductions and seeing all sorts of basic context of everything we're studying within this whole grid forming, low inertia grids topic area. So I'm going to just skip all that and say, okay, I think we've all done that basic introductory part, and we want to just dive into some technical stuff. And so there's three main topics I'm going to talk about today. And the first one is I'm going to be talking about how we can use grid forming single phase inverters to build up three-phase systems. And the key idea here is these single phase inverters are each doing their own thing, yet when you connect them together, due to the grid forming function, they actually can perform automatic phase balancing. So you can get three-phase systems by interconnecting single phase units. And this is the latest thing I've been diving into. And then I'll take a step back, and next I'll talk about the dispatchable virtual oscillator controller. That's kind of the latest and greatest of the virtual oscillators. So I'll do a little bit of history and talking about just oscillator circuits and what brought us to the present moment where we're using this so-called DVOC controller. And then the last thing I'll do is talk about how we can take a mix of different control types of grid forming functions. So this can be droop controllers, virtual synchronous machines, virtual oscillators, and have them all play together and work together as a functional AC power system. So we'll work through all three of these, and I'll have an experiment to showcase each one of these. And I've been working on a new format to show experiments with videos and stuff. So I hope you all appreciate that. Okay, so let's go ahead and dive into this concept of phase balancing. Okay, so before I dive into that, I want to mention that if you want to find a single phase grid forming commercial product that you can buy and connect to your house and actually see it do its thing, this is Enphase's product. So they have this entire concept they're calling Ensemble, where the vision is having PV, energy storage, and being able to flexibly assemble microgrids from the ground up, from the home level up to neighborhoods, and conceivably up to very large systems. And Donnie walked us through some of this. So let's imagine that we had a distribution system with that is dominated by single phase residential loads, like a bunch of homes or houses. And let's say you just sprinkled a bunch of N-phase inverters all over that grid. Now, also suppose here that we have some substation with a step-up transformer, and let's say there's a disturbance on the grid, and we have full faith that our grid forming units will be able to keep this single phase distribution, or this distribution system, which has 3 phases, but single phase loads hanging off of it. We have faith that they will have uninterrupted power by the grid forming units. Now, the interesting thing here is that if you island this whole system, I also want to throw in the idea here that there are no 3-phase units. Suppose it's just all single phase grid forming inverters. Could they maintain phase balancing where they're each pushing each other 120 degrees apart and maintaining 3-phase balanced voltages? And that's important because you might have some 3-phase loads on the system that do need balanced 3-phase voltages. So that's the question, and I wouldn't be talking about it if the answer wasn't yes. But what's really fun about this is that the grid forming units that live on the same phase, let's say that you have a bunch of units on phase A, they will give you what you expect from a grid forming unit. They will power share, they will synchronize and work together. Same goes for anything on phase B as well as phase C respectively. But the magic is that the phases are interacting with each other and also maintaining balanced operation. So let's go ahead and dig into that question. Now, that system I just showed you of a full-blown distribution system, maybe a 4-wire system on one side, and then we have a delta connection on the other side, transformer dynamics. That's something that we are studying, and that's the long-term objective, is to fully characterize that. Now, we're just getting the first paper off the ground on this, and we wanted to start with something a bit more fundamental so that we can understand the fundamental dynamics of how the system works. And our observation here is that you need a delta connection somewhere on the system for this concept I'm describing to function. So the simplest setup that we can study is taking 3 single-phase grid-forming units, as shown here, connecting them directly in delta, and then connecting loads across them. And those loads can be connected in whichever configuration you want. So again, this is just the most simplistic setup, and we're using it as a launching point for this whole line of work where we want to study that more realistic system I showed on the prior slide. Okay, so if we go ahead and dig into the Droop controller, this is just a fairly standard Droop controller that we've seen in other presentations. So here is a single phase voltage source inverter, nothing too special about it. Here we're measuring the output current and output voltage, performing calculations to measure real and reactive power, standard filtering to get a clean measurement. These are real and reactive power biases, and then there's the actual Droop laws themselves. And then finally, we get an amplitude and angle that can be used to synthesize a sinusoidal command. And then here I have abstracted out inner loops. So suppose that we want to take this voltage command and make sure that it appears here across this capacitive branch. So here we'll have fast inner loop controllers that take this voltage and current measurement and ensure that this voltage command is being realized right over here on the output of the capacitance. Okay, now if we're standing over here at the terminals where you connect the rest of the grid or the upstream system, when you stare into these terminals, we're going to model everything that's in this point as here's the phasor circuit model. So here's a voltage behind some reactance and resistance, where this L and R correspond to this X and R. And the amplitude and angle of this are dictated by the Droop dynamics. And if we take this simple representation here and we unfold it and we connect 3 instances of that to get a delta connection. So here is one instance of this top left diagram. And then here are two others. So these are three single phase Drupe converters with this exact implementation, just drawn in a simpler format. All right, and then here we're just showing how the system looks like with a Y connection, where Z load is just some arbitrary load impedance, and then there's some currents that we can define using that will facilitate analyzing the various loops within the circuit. All right, now if you work through Kirchhoff's laws and you work through the Drupe equations and you do all the algebra and make all the appropriate substitutions, what you will find is that you end up reaching these following dynamics. So VL and theta L dot, this is the amplitude of the produced by the Drupe law, and theta L dot is the frequency also produced by the power frequency Drupe. And then Z loop here is just denoting that if you look across this delta loop, these are the output filter inductance and resistance of each inverter. And if you just total this up around the entire loop, that's what this Z loop quantity is. And MP and MQ are the Drupe slopes for the reactive power versus voltage and real power versus frequency Drupe laws. All right, so this is I think a pretty neat looking equation, and we're summing across three indices. I could have called these A, B, and C, but I just gave them number indices since they're all independent from each other and just doing their own thing. Now, if we go ahead and look at the angular differences, so let's say we want to look at the angle difference between units 1 and 2 and 1 and 3, which I'll denote as theta 2.1 and theta 3.1. And we look at their dynamics and work through all the algebra, we're going to end up with some terms that have products of small quantities. So MP and MQ are the Drupe slopes. Those are generally pretty small numbers. And if we go ahead and neglect those terms, these are the dynamics we get for the angle differences, where K is just some constant. And what's neat here is that if you've studied oscillator systems, this equation up here looks a lot like the Kuramoto model, but here we have a sign flip in front of this term. And that's important because whereas with a Kuramoto model, we get attractive dynamics with angles pulling together, here we get repulsive dynamics where things are pushing each other apart. All right. So now what we're going to be doing is connecting three copies of this, and these are this is showing the phase portrait in two different formats. So these red and blue surfaces are showing the derivatives of the angle differences between units 2 and 1 and 3 and 1. And we only need to look at two sets of angle differences because there's 3 units in the system. And if we look at where the equilibria are on the system, so we can take this surface on the bottom and find where we have stable and unstable points. We're just analyzing this numerically. Here's what we end up seeing is that the configurations with the black dots indicate stable points. So this is analyzing the linearized system and stability at those particular points. So we first compute the equilibrium of the full-blown nonlinear system and then linearize at these various equilibria. So we have these stable points here. We have saddle points here. You can see how the dynamics flow in and out of those. And then we have unstable points where we have dynamics flowing out of those. Now, the important thing to see here is that we have these two stable points, and these are actually the two stable points that coincide where we have 2 pi over 3 angle differences between the units. So anywhere you put this in terms of an angular initial condition, they will eventually drift and reach that point. The only thing you got to be careful with is the phase ordering. So if you want to have A, B, C, and these are 3 arbitrary units, they don't know each other exist, you can end up with a phase swapping. So that does have some implications of how you start the system up. Okay, all right, so that's the general idea and what we're putting in our first paper. And here's an experiment that is more aligned with the practical distribution system I was trying to show earlier. And so let's go ahead and take a look at this experiment. So what you're about to see is a live action video. So the oscilloscope waveforms will be moving in real time. This is time synchronized, where you'll see Minghui, who's one of the postdocs in my lab. He's actually running the experiment live. So this is like a little performance we put on for you all. And all of the waveform color codings here match up with what you see on the left-hand side. So the voltages produced by the three droop-controlled grid-forming units are V1, V2, and V3 here. They're on the top. And our goal will be to show you that we will reach a phase balance condition. I1, I2, and I3 are the currents coming out of the droop units. And then we also have a transformer that has a Y connection on one side and a delta connection on the other. So we do have a line-to-line voltage as well as the current on the other side. Okay, yeah, let's go ahead and let this thing play. All right, so initially, the voltages are unbalanced. And what he's about to do is he's going to close this switch. And this switch is what will introduce the presence of the transformer. And it is the delta connection that they're now interacting with, which is what allows them to reach the balance condition, okay? So we basically have currents flowing through this transformer, through the delta side, and that is giving the physical coupling that allows them to reach the balance condition. So that should have been the oohs and ahs right there. You can see that indeed they are 120 degrees phase separated with respect to each other. Now he's going to step the load here on the secondary side. So nothing too exciting here, just showing that we can deliver three-phase power to a load on the secondary side, and then he's removing that load also. And the whole time we have a local load here. Now the next thing he's going to do is going to introduce some imbalance on the virtual layer. So there's power dispatch set points. So he's going to give a large power command to the first unit. So there's a step up. And you can see that the voltages are pretty robust. The angles don't drift very much, nor do the amplitudes. And we do see some imbalance in the currents. And there's some interesting stuff, I think, to be studied here because this is a 4-wire system. And here he stepped it back down. So here we're back to balance conditions. So you can call that a cyber layer imbalance that we just saw from the power dispatch set point. Now he's going to introduce a physical imbalance and throw a load on the phase A. There you go. And again, we see nice balanced voltages, whereas the currents have the imbalance. All right, and he's going to remove that. And then that will conclude the experiment. Okay, all right, so that's the first experiment and concludes the first part of the talk. Oh, let me go back to full screen, sorry about that. Okay, all right, so now we're gonna be moving on to part 2 of the talk. And I'm gonna give basically a short tutorial on dispatchable virtual oscillator control and show an experiment where we will have multiple power converters using this control strategy. Okay, so let's jump into this and we're gonna dive into the history books a little. It should be fun. All right, so some notation for reference frames are shown here. So actually in the remainder of the talk, we're gonna be dealing with 3-phase systems quite a bit. So this is just establishing a vector for a 3-phase balanced voltage. Frequencies of the actual power converters I just denote as omega, whereas the nominal frequency is omega naught. And then this is just giving us the instantaneous angle, and we can also define angle differences if we want. The last thing that's going to be popping up are some coordinate transformations. So we have ABC to DQ, as well as a rotation matrix. So ABC to DQ transformations are done with Parkes transformation. Here's the format where I've ignored the 0 axis because I'm assuming balanced operation for these models I'm about to show. And R of theta, R of X is going to denote a rotation matrix. So if you're in a 2D space, this is just rotating by here. This would be some angle I'm just calling X. All right, so let's begin by just looking at the simplest thing. All right, so physics 101, where you learn about circuits, we all know and love the harmonic oscillator. And if we just draw the circuit, it's just a parallel LC tank. Of course, you can do a series one, but we're going to be looking at the parallel version. And we can just define two variables. I'll call them X1 and X2, where one of them is the capacitor voltage, and X2 is a scaled version of the inductor current, where I'm scaling by this parameter I'm calling epsilon. That's the characteristic impedance. And of course, this thing resonates at 1/√LC. And you can write it in this, the diffie is in this really simple form up here. Okay, so that's the most simplistic thing. And now what we're going to do is we're going to introduce a nonlinearity into the circuit. And that's where Mr. van der Pol, who was doing his research in the early 1900s, was studying this circuit. So you can see his publication from the 1920s, where he was playing with vacuum tube circuits and stuff like that. And he noticed an oscillation. And essentially what this gives you is a self-sustaining oscillation, so that any arbitrary initial condition, it always reached the same limit cycle or oscillation. Whereas the harmonic oscillator, the oscillation depends, or the size of the oscillation depends on the initial condition entirely. This one, irrespective of the initial condition, we always reach the same oscillation. Okay, so IM is just what I'm denoting as this dependent current source that's in the model. So this thing depends on the capacitor voltage, and he was observing this effect in these vacuum tube circuits. And what's neat about this is we have work from 2014 and 2020 where I was looking at this, as well as people from North Carolina, as well as others across the world using the van der Pol circuit for controlling power converters. Okay, now one problem with this is this oscillation has a wobble to it, and this gives us some harmonics that cause us to have to devise solutions to fix that and get better power quality. So that's not as good. So the other oscillator we're looking at that doesn't have that wobble is what I'll call Andronov's oscillator. And this comes from some modeling work from a Russian scientist. And yeah, his works were translated in the 1970s. And basically he has a model that is just a richer version of the van der Pol oscillator model. And in fact, I drew it like this because if you look at the van der Pol model, it's basically just a higher dimensional version of it. It actually is, you can say, hiding inside of Andronov's oscillator, but it's still a very similar idea. And here in the model, you can see that we have some dependence between some nominal amplitude that we pick and the instantaneous oscillation amplitude. And irrespective of the initial condition, it will always spiral out to this black trajectory shown here. Okay, so now what we're doing is we're going to take that nonlinearity and actually put it on the inductive branch too. And what this does is it gives us a more symmetric set of dynamics. And what this is doing is really laying the groundwork for what I'll call like a three-phase implementation. So let's say that you wanted to connect this kind of abstract oscillator circuit to a three-phase load, then you would do something like this. Okay, so those dependent current and voltage sources I just replaced with these diamonds, VM and IM. And what we can do is we have naturally existing orthogonal variables, X1 and X2, that are separated by 90 degrees. We have a voltage scaling, and we can use that to issue a voltage command. And we can use a coordinate transformation to control 3 voltage sources. And if we have a 3-phase current, we can then use that same transformation in the stationary reference frame to get some currents, and we can feed that back into the oscillator like this. Now, this is really what I'm showing is moving us towards the dispatchable virtual oscillator controller. And the last thing I'm throwing in here is I threw in some current bias signals that allow us to have real and reactive power dispatch set points is shown down here. This is just some scalings where we're taking real and reactive power commands and converting them into current biases. And if you look at the diff EQs for this system, this is what we get as shown here on the bottom. All right, now this circuit, if you actually want to control a power converter, you can just basically drop in those ideal voltage sources and replace them with a power electronics stage like this. And you just need to apply some PWM. And that's how you would actually do this on real hardware. Okay, so this is where we're connecting things now to just a few years ago, 2017. We had a really nice paper coming from Florian and Dominic and the team at Zurich at the time. And so I think this is probably the direction that's probably gives us the best performance in terms of one of these oscillator type of implementations. Okay, now if this nonlinear circuit just feels strange and it's just not pleasing to look at, I think there's a really nice way to study this that just looks a lot easier. So if you just go from the stationary coordinates where you have orthogonal sinusoids, a pair of orthogonal sinusoids, you can define an amplitude and an angle and just look at the same diff EQ. So it's still second order, then you end up with this format here. And you can see that the voltage dynamics, we basically have something that resembles a voltage error in this first term. And then we have two additional terms that basically just give us a weighing between reactive power mismatch and real power mismatch, where these starred quantities are commanded values and P and Q are the measured values. Okay, and then what's shown up here is this is your frequency equation, which looks like just a frequency droop. So this should look a lot more, you can say standard or typical of what you would expect the power interface to operate at. And you can actually implement it like this. So this is not only, I think, easier to look at visually, but you can also code it up like this. You can use DQ transformations and actually code up your controller like this. Okay, and then if you set all those derivatives to 0 and just look at the steady state, then you'll see that we have what look like just standard droop-like curves. And in fact, the frequency versus real power curve, and this is for this rotation matrix being set to 0 degrees, we get a real power versus a frequency droop. It looks perfectly linear, just like a standard droop equation. And then we also have a reactive power versus voltage droop equation. And this one it's pretty close to linear for most of this region. And here we've drawn it to accentuate that there is a little bit of nonlinearity that you have to contend with. And this is the solution if you just set these derivatives to 0 and just do some algebra. Okay, great. So that hopefully gives everyone in the audience an idea of how this virtual oscillator stuff works. And the next thing I want to show you is how we can build up a 100% inverter-based system using this control.
Hey, sorry about that. I didn't have two headsets going, but I had a Zoom meeting going on at the same time, and I had no idea how to make it stop talking.
Oh, okay. All right.
So what's up?
Do you have a question, or should I just continue? All right, I'll continue.
Ooh.
Okay. All right, so here I'm going to show a video. This is an experiment with 3 dispatchable virtual oscillator controllers. I'll be showing a little power meter above each one of these. So you'll see little arrows above it where if it's pointing to the right, this is delivering positive real power. If it points to the left, it's absorbing real power. I'll be turning these on and off, so you'll see the red and green colors change. Here I have a stiff grid, so we can go from grid connected to islanded mode and introduce load steps. I even have a little frequency meter here, so you can see the frequency move up and down because there is frequency droop. And you can also see it here on the scope too. We have really fancy scopes that give us nice waveforms that we didn't have back when I was in grad school. All right, and here's these two characters, Mingwei and Rahul, who are going to be running around and doing the experiment. Okay, let's see here. Go to the next slide. Okay, so we start off, all three inverters are turned off, and here is the first one. You can see that it's just producing a voltage. There's no current coming out of it. It's hiding behind an open circuited switch. So let's go ahead and close the switch. We're commanding 0 real power, and the frequency is being rigidly held by the grid simulator. So that means that when we close the switch, you should see that indeed there is practically 0 watts coming out of the first unit. There's a tiny bit of reactive current flowing around, but that's no big deal. In terms of real power, we're getting no real power flowing out of this thing. All right, then in a second here, Mingwei is, he issued a power step up command. You can see the current go up, and indeed it's following the power command. Again, the frequency is being rigidly held by the grid, which means that due to frequency power droop, commands and actual powers should follow each other. All right, so now we turn on the second unit. Now notice this thing drifting. That's because of the power frequency drift. There's a frequency mismatch. So you're going to see this thing drifting around. Oh gosh, my video is being a little glitchy. Hold on, let me back up a little. You need to see this moment. Okay, so Rahul, what he's doing is he's flipping this switch and he's just using his eyeballs to gauge when these crests are lined up, just like kind of the classic light bulb experiment. And you can see now that they're power sharing, or actually they're both following their power commands is probably the more accurate way to put it since they are grid connected. All right, next thing we'll be doing here is here's just another power step on the first unit. You can see its current dropped. All right, next thing we'll be doing is we'll be islanding the system. Okay, now because we have no clue what the load is, real loads are always unpredictable. There will be some frequency droop kicking in, and the real power versus commanded power values can now deviate from each other. Okay, so here the frequency gives us an idea of how far off we are. Okay, finally, we're turning on the third unit. You can see Mingwei here is, he's eyeballing the scope. He's really, you can see the intensity in his eyes as he's making sure those waveforms line up, and then he closes the switch right there. All right, so there we go. We have a nice power, equal power sharing from the two units have the same commanded values. All right, and then here we're going to be looking at a power step up in unit number 3. So you can see that the current went up on the third value. Now here, this is the interesting part, so get ready. So what we're about to do is we're about to disconnect this heavy load. That's why I made it look nice and chubby. And when that happens, you're going to see that there is a large disparity from the first unit compared to the second and third unit. And in fact, the first unit has a small power command compared to the last two units, and you're going to see a reverse power flow. Because what will happen here is once we remove this load, in fact, what's happening is the second and third unit are powering this puny little load, and whatever's left over actually back feeds into the first unit. So if you had batteries there, you could just charge batteries now. All right, and then now we just step up the first power command to give us equal power sharing. Okay, all right, so that's that experiment with the dispatchable virtual oscillator. All right, and then to close out, I have one more set of analysis and experiments to show, and this is really about this idea of interoperability. And so let me just take a brief detour here and mention that in the Unify consortium, we're thinking about how are we going to pull this off? How are we going to bring a whole industry on board and get all these manufacturers and control types to work together? And it was actually in those early conversations that Deepak Devan had the brilliant idea. He said, we need to emphasize interoperability more than anything. And we really ran with that concept. And this set of experiments and analysis are meant to highlight how important that concept is. And I think it's really going to be the idea that that paves the way for the industry. Okay, so part of this is a little bit of review because we've already seen Droop control and virtual oscillator, but let's do it anyway. So here is just Droop control, the classic method that's been, I guess, the workhorse of grid forming for several years. And there isn't much to discuss here because I already talked about this, but here's showing a slightly different implementation from before, where we have ABC to DQ transformations, but it's basically the same thing I showed for except the three-phase version instead of the single-phase version I showed in the first part of the talk. And here are just the Droop laws themselves. And here's that rotation matrix that I'm sneaking in there. And that allows us to dial in the degree to which the voltage and frequency Droop laws are acting on real and reactive power. So you can actually get a blend instead of the extreme of one or the other. Okay, and for just convenience, I'll be just drawing this cartoon in a cartoon-like fashion as just a blue box with a line through it to indicate the Droop laws, and these are the equations. And I just rewrote it in a slightly different format because I'm trying to actually show that all three of these do have a similar form of all these different grid forming control types. Okay, so here are the Droop slopes, except I wrote them as inverses. The last equation here is capturing those low pass filters we use to perform signal conditioning on the measurements. Okay, all right, so the next one is virtual synchronous machine control. And I'm doing this chronologically. So first appeared Droop on the scene in the 90s. And then roughly around 2007-ish, we have the virtual synchronous machine control. And here, if you're a machines kind of person, this is a really neat and convenient controller to work with. And here, we do have a phase lock loop sneaking into here. But other than that, it has a similar form to the one I showed. And the reason the PLL sneaks in here is because we do have like a damping term that sneaks into the swing equation. So we do have full swing equation dynamics here, which is emulating Newtonian mechanics of a rotating mass. The voltage equation looks like the standard static Droop equation. And then we have a couple equations here for the phase lock loop. And then finally, some signal conditioning for measuring reactive power. And because, of course, we're emulating a machine, I'm just drawing this as something that looks like a rotating machine here in a cartoon-like fashion. Okay, finally, there is the dispatchable virtual oscillator controller. This is, like I said, what's appeared on the scene in roughly 2017-ish. And this looks a lot like the DQ version that I showed in my tutorial earlier. So I'll just kind of move ahead, and we're just rewriting it slightly differently to emphasize the notation here. And the reason I'm rewriting like this is you'll see that I can take all three of these control types and describe them in a similar form. And from a diagrammatic perspective, I'm just representing this as an oscillator circuit. Okay, so the idea here is that if you have any three of these control types, you can write them down as this same set of diff EQs. And the way to realize the Droop controller or virtual synchronous machine or the virtual oscillator is just to tune the coefficients of this set of equations appropriately. And this table here shows you how you could realize any three of these grid forming controllers by just parameterizing this appropriately. Okay. And this is to show, again, the similarity of the three of these from a steady state standpoint. So they They do differ from each other from a dynamic standpoint, but when you look at steady state performance, you set all derivatives to 0, and you look at real and reactive power trade-offs versus frequency and voltage, here is what you get. Now, one thing to note is the virtual oscillator has these kind of reddish to yellowish color hues to them because it has a different shape to it due to its nonlinearity, whereas the Droop and virtual synchronous machine have the same steady state characteristic. And even though there are differences there, you can see that they're relatively small and that essentially all three of them do have a very similar steady state behavior. And here on the top, I'm showing what happens when you pick this rotation matrix to be 90 degrees. You generally do this for highly inductive transmission lines between your inverters, and phi being 0 degrees for resistive lines. Okay, all right. So, okay, so one thing that I'm looking at this, I think what's neat about it is we're trying to unify 25 plus years of work on grid forming technologies, and really showing that even though these three can look like very different animals, there is a common structure to them. And from an implementation standpoint, I'm trying to actually streamline some embedded code development along these lines so that we can realize any of these three controllers with ease. And again, I think this just highlights how all three of these controllers can work together. And I think this can pave the way to some really advanced modeling for systems. Okay, finally the experiment, and then this will be the last thing I show. All right, now this experiment, I'm gonna be pulling something out I didn't earlier. So here we have the dispatchable virtual oscillator, we have the Droop controller, and then we have a grid following unit. So this is just a standard grid following unit that has a phase lock loop and a current control. And this represents, you could say, legacy converters that will be on the grid for many years that have fully functional grid following functionalities, and just showing that all of these work together. If I had time, I would have run another experiment with a virtual synchronous machine and had 4 of them together. I think that's hopefully what we're working toward in the near future. And it's the same format as I showed earlier, except I just streamlined things a little bit, but we'll be turning units on and off, and we have the color codings matched up here. And here, Wei Chen was the brilliant student who ran this experiment. All right, so let's get this going. Gosh, my video is so glitchy here. Hopefully that's coming through to you guys. All right, so here the first unit turned on. It's delivering current to an islanded load. Now in a moment here, he's going to turn on the second unit. So he's going to his computer and going to turn on the Droop controlled unit number 2. Due to frequency droop, they're drifting around, which is why you can see them moving against each other. Now he's eyeballing the scope, and he's going to close this switch whenever he gets those waveforms lined up. There you go. They have the same power command. So this is important. We have power sharing between heterogeneous controllers working together and interoperating as a system together. All right, he just issued some load steps here. So you can see the power demand went up. He just added this load. All right, next here, we're going to be seeing the grid following unit turn on in just a moment. My screen updates, my goodness. I think Zoom is killing me, guys. This was working fine a second ago. All right, there we go. We have a 0 current command. He just stepped that up. The grid following unit doesn't know whether it's following a grid or grid forming units. It doesn't care. It just latches on, injects currents, and can follow current commands. And for the grid forming units, the grid following unit just behaves like a negative load. Wow. All right. Okay, well, Gosh, yeah, if it wasn't for my video being really slow, let me try one more time to see if you can see the end. All right, here's where we have a large current command from the third unit, and then we turn this off, and then the other grid forming units step up and power up the load. Okay, all right, that was my last slide. I guess at this point, let me see here. Happy to take any questions.
Thank you.